All right, we should be recording here. Let me just double check. Perfect. All right, so this is going to be the tutorial video for a lab that you're going to do. We're going to look at statistical applications of some of the multivariable extrema that we have been exploring in our calculus class lately. And I like this because data science is one of the most growing fields right now in terms of just employment in general. Lots and lots of people are going into statistics and data science in order to look at model fitting, whether it be in the business world, in the social science world, in the physical science world. Statistics is a really growing field, and data science is a really growing field. So I think you'll get a lot out of this lab. So I just kind of want to start. Everybody's has a slightly different background in how much stats they've had. So kind of looking at this from the perspective of never having had a statistics course, even though I know some of you are probably even taking AP Stats right now. Some of you have probably looked at how to graph a best fit line, whether it be in a previous math class, in a science class, you might have done a lab or an experiment where you had to fit data and come up with a best fit line in order to model that data. So we're going to look at a little bit of a process that's called linear regression. Or really in general, the process is called least squares regression. And I'll talk about why it's called that in a little bit. But it's one of the most widely used fields in statistics and data science is finding the best possible model for a set of data in order to make predictions, whether it be for the future or even for current values. But how do you find the best possible model? And this process takes quite a bit of time. So we're going to kind of simplify it here. But there's several ways to develop such models. And one of the simplest methods that people usually try first is what's called the method of least squares regression. And typically the model you would try to fit first for a set of data would be a line. And this is what you would have done, as I said, in a previous math class or in a science class. You drew what was called a line of best fit. And what you were basically trying to do is if you had a set of data points that you graphed, this is what's called a scatter plot. It's where you plot all the data points on the graph. Here's your x-axis, here's your y-axis. X would be your independent variable, y would be the dependent variable that you're trying to measure or predict. You know, you got a bunch of data points that you collected from a lab, and you're trying to find the line that best fits that data. In other words, you're trying to find a line that you can draw so that the data points are as close to that line as possible. It's the line that tries to best accommodate all of those data points. Now, it's not going to be able to make all of them happy, right? There's no way that you could draw a line where all of those dots fit perfectly on the line, but you do the best you can. And so, you know, I'm estimating right now, is that the line of best fit? How do I know that's the best possible line I could draw? How do I know that that's the line where all of the data points are as happy as they can be or as close to that line as possible? How do I know it's not this line? Or I'll do a different color. I'll do one more. How do I know it's not this line? I'm eyeballing it right now, right? I want to come up with a mathematical way where I can guarantee that the distance between those data points and the line, if I was to drop a distance, a perpendicular distance from the dot to the line, how would I know that I'm minimizing that distance? And so that's really what we're going to go into with the calculus here, is trying to minimize those errors, those vertical distances between the data points and the actual line where those predictions lie. Okay. And so let's kind of formalize this a little bit. As a way to measure how well our model, we're going to call that model y equals f of x, fits the collection of data points. So each one of these is a data point. x1, y1 would be the first data point. x2, y2 would be the second data point, so on and so forth. We're going to say that we have n data points. And so in statistics, typically what we do is we let n represent the sample size. So we're assuming that we took a sample of n data points, each with an ordered pair x sub I, y sub I. What we can do is we can add the squares of the differences between our actual y values, those are our data points, and our predicted y values that we would get by plugging the x value into our model of best fit. And in this situation, we're going to be using a linear model for the first part of our lab here. And so I'll get into that in a little bit. But in general, if our model's just y equals f of x, it could be linear, it could be quadratic, it could be a sine wave, it could be a logarithmic function. This is really just whatever model you want to use. And statisticians in practice try many, many different models using many different techniques. But every single model you use, you can use this strategy, and it's called taking the sum of the squared errors. Okay? In other words, we're going to take the distance between the actual y value which is y sub I, and the predicted y value, which is what I get when I plug my x value, my independent variable, into that model, f of x. This distance right here is what's called a residual. This represents your error between the actual output and the predicted output. So if you were graphing your line of best fit, for example, this would be your actual y value, and this little star that I'm putting right here would be f of xi. That would be the y value that you get from plugging into the line of best fit. Now, clearly you can see the data point doesn't lie on the line, right? So this little vertical gap right here, that difference between the actual y value and the predicted y value, that's your residual. Now, the problem is if we just add up all those residuals, if I was to add up all of these little residuals, every single time you do this process, the sum of those residuals is 0. And so you wouldn't be able to minimize just the sum of errors because the sum of errors is always 0. Calculus wouldn't even work on this. So what we do in order to get some calculus going, in order to minimize these errors, is we end up squaring those differences. We end up taking the sum of these squared residuals, because when we square them, they'll end up being always positive, and then we'll actually get a function that we can minimize. So instead of summing the errors, we sum the squared errors. Okay? And you'll notice I reversed the order inside the parentheses here. It'll just make our calculations a little bit simpler later. You could very easily do the actual residual and square it, but it just ends up giving you more negative signs than you would want. So because we're squaring it, we can reverse the order. It's going to give us the exact same result. So graphically, as I mentioned, this can we're going to call this function s. Okay? S is going to be our sum of squared errors. S can be interpreted as the sum of the squares of the vertical. Oh, that got a little bit too small. Let's do this. There we go. S can be interpreted as the sum of the squares of the vertical distances between the graph of f and the given points in the plane, as shown below. I just came up with an example here that I graphed for you. Now, if the model's a perfect fit, all of those data points would ideally lie on that blue line, right? So you'd have a line, every single data point. If it was a perfect rise over run every single time, there would be no vertical gap between the dot and the line because the dots would lie on the line. And so in other words, all the residuals would be 0. So if you sum up 0 squared plus 0 squared plus 0 squared n times, your sum of squared errors would end up just being 0. Now, in practice, when you're doing this with actual data, perfection is not feasible, right? And so you settle for a model that minimizes the sum of those squared errors, the sum of those squared residuals. And that's, again, what I was describing before, is you want to try to make the distance between the data point and the line of best fit as small as possible, or whatever model you're using, even if it's not linear. So here's an example with 4 data points. In this case, n would equal 4, sample size 4. If you look at the data points we have, it looks like we have points at 1, 6, let's see, 2. I wrote some of these down just to speed it up a little bit. Looks to be about 2, 5, 3, 7, and 4, 10. So those are the actual data points. Those are, this would be my y sub 1, my y sub 2, my y sub 3, and my y sub 4. And then using the model, I can predict using what's on the blue. Let me kind of pick a different color here. Let's pick green maybe. Here's my first prediction. Looks to be at about 5. So my first f of x1 would be about, it's a little bit lower. I'll call it 4.8. My f of x sub 2, these are my predictions, would be about, looks to be overestimating, right? Because it's higher than the actual y value. That looks to be about 6.4. My f of x sub 3, let's see. F of x sub 3 looks to be about 7 point, what did I use? I used 7.75. And again, I'm just estimating right now just to give you an example. And then the last one, f of x4, looks to be about just over 9. We'll call it 9.1. And so all I'm going to do is I'm going to sum the squared differences here. Well, each of these gaps or these residuals we're going to call d sub I. So d sub I represents the ith residual, the ith error. And so the sum of squared errors would be d1 squared plus d2 squared plus d3 squared plus d4 squared in this case. So what we're going to get, this is approximately using the estimations from the blue line that I used, actual y value 6 minus prediction number 1, 4.8 squared, and then we're going to do it all 4 times. So then I would get 5 minus 6.4 squared plus 7 minus 7.75 squared plus 10 minus 9.1 squared. If you throw that all into your calculator and you estimate it, you get about 4.77. Okay. And so this would be the minimum sum of squares, and this model would be the one that best approximates the data, at least for a linear fit. Okay. So now the question is, well, how do we come up with this model? How do we end up finding this sum of squared errors? And so that's what we're going to do here. Is we're going to look at this for a linear model. Statisticians, data scientists, they call this linear model that minimizes S, the sum of squared errors, the least squares regression line. Sometimes it's abbreviated LSRL. And so our goal is we want to use techniques that we've been exploring in section 14.7, right? We've been looking at how to find multivariable maxima and minima, extrema, on a given domain. And so we're going to do this for a line. So we've recently learned how to find values of a and b that minimize S for a line f of x equals ax plus b. So we're trying to find values of the line that give us a slope, which we'll call A, and a y-intercept, which we'll call B. We want to find the values of the slope and y-intercept that minimize the sum of squared errors for this linear model. So we're going to define a function, S, which depends on 2 parameters, A, the slope, and B, the y-intercept, to represent the sum of the squared errors for this linear model, f of x equals ax plus b. And we're going to assume there's n data points, x1, y1, x2, y2, all the way up through xn, yn. And so let's come up with a formula for S of AB. Okay, remember, what we had was that it was the sum from I equals 1 to n. All right, we have n data points. Okay, on the last page, we called it f of xi. Well, in this case, f of xi, if I go off to the side and do a little scratch work, that would be axi plus b. Okay. So this right here is my f of xi, and then I was subtracting the actual y value, which was y sub I. And then I'm squaring it. So remember, the residual itself, we do the opposite order. We do the actual minus the predicted. So that would be yi minus axi plus b, but as you can see, that's going to lead to more negative signs than we want. Since we're squaring, the order doesn't matter that we subtract in for minimizing this function. So this is going to be the function, I'm going to highlight it. This is the function that we're going to be minimizing, is this sum of squared errors right here. And we're regarding the points xi, yi as constants, since we are minimizing this function of a and b. A and b are our variables in this case. The slope and y-intercept are what we're trying to figure out. Okay, so xi, yi are just constants. And so to minimize S, we're going to use the strategies from section 14.7. First thing we have to do is we have to compute the partial derivatives of this function S of AB. So I'm going to compute S of A, or S sub A and S sub B. Okay, now, if you remember from Calc BC, if you have some type of power series representation inside of a series, you can differentiate and integrate. We're not going to do any integration here, but you can differentiate and integrate within the summation. And so that's exactly what we're going to do here, is we're going to be taking derivatives within this sum. So the first one I'm going to compute is the partial derivative of this sum of squared error functions with respect to the slope, A. So S sub A, if I take the partial derivative with respect to A, really what I'm going to do is I'm going to bring the power down in front. So I'm going to get sum from I equals 1 to n of 2 times, I'm going to leave the inside function alone, axi plus b minus yi, this will now be to the first power, and then using the chain rule, the derivative of my inner function would be x sub I, because I'm differentiating or partially differentiating with respect to A. Okay, let's clean this up a little bit. So this would end up being the sum from I equals 1 to n. I would end up getting, 2 xi, I'm going to move the xi out front here, times axi plus b minus y sub I. And so if I distribute here, I get the sum from I equals 1 to n of 2a x sub I squared plus 2b x sub I minus 2x sub I y sub I. Remember, a and b, this summation only depends on indices for x and y, so any coefficients I can pull out front. And remember that this summation is a linear operator, so we can actually split this into 3 separate sums. So if I do that, this would turn into the 2a can come out front for the first sum. That's a horrible summation symbol. Let's do that again. I get 2a sum I equals 1 to n of x sub I squared. So we're adding up the squares of the x coordinates, plus 2b sum I equals 1 to n of x sub I. So there we're adding up just the x coordinates without squaring them, minus 2 times I equals 1 to n x sub I, y sub I. So that'd be the sum of products of the x coordinates and the y coordinates. Okay, so there's our partial derivative with respect to a, and now I'm going to do it one more time for b. So s sub b, this one's a little bit easier. If I go back up to my sum of squares function, the partial derivative with respect to b, I'm still going to bring the 2 down in front, but in this case, it's going to be a little bit simpler because the derivative of the chain inside would just be 1. So I'm going to get the sum from I equals 1 to n of 2 times axi plus b minus y sub I to the first times 1. And so if I distribute here, this would give me 2a can come out front, sum 1 to n xi, I equals 1 to n. I'm going to explain this one in a second. 2b, we can actually simplify that one a little bit further. Minus 2 sum from 1 to n of y sub I. Okay, I'm going to move myself out of the way here. Move me up. Well, maybe I can't. Okay. So this one, it only depends on b. There's no indice x sub I or y sub I. So think of it as you're really just adding up 2b n times, right? So you're doing 2b plus 2b n times. And so this one we can actually simplify. This would be 2a sum I equals 1 to n x sub I. This would just turn into 2n times b. And then minus 2 I equals 1 to n y sub I. So there's our partial derivative with respect to b. Okay, pause there if you need to go back and take a look at anything before we move on to step 2. Okay, so step 2, we have the partials. Now we want to find the critical points. If you remember from our discussion in section 14.7, the critical points would be when those first partials are equal to 0. So my goal right now is I need to find values of a and b, that's that desired slope and y-intercept, such that s sub a equals 0 and s sub b is equal to 0. This is my goal. Haven't done it yet. Okay, so basically, what does that mean? We need a and b such that, okay, so here's where we come into using the partials that we just calculated. Our s sub a, if you remember, was 2a, make that a better a, 2a, sum I equals 1 to n, xi squared plus 2b sum I equals 1 to n, x sub I minus 2 sum I equals 1 to n xi yi. We need that to equal 0. And we need s sub b to equal 0. That was 2a sum I equals 1 to n x sub I plus 2nb minus 2 times sum, my sigmas are not good today, I equals 1 to n y sub I. I need that to equal 0. Now you could work with these two functions, but if you'll notice, every single term has a coefficient of 2 in the first equation, so we could divide out 2 from both sides, and that's what I'm going to do. Similarly, in the second equation, every single term has a coefficient of 2, so I could divide out 2 from both sides. It'll just make the calculations a little bit easier, and it'll save me some easier divisibility later on. So I'm just going to say, or equivalently, we get If we divide out 2 from everything, we end up getting a times the sum of I equals 1 to n x sub I squared plus b times the sum from I equals 1 to n of x sub I. And what I'm going to do is I'm dividing by 2, but I'm also going to move this term over to the other side. So once I divide by 2 and move that over, and you'll see, the reason I'm doing this is because I want to end up using elimination to solve the system. So this would be sum I equals 1 to n xi yi. Okay, so I divided out the 2's and I added this term over to the right-hand side. And I'm going to do something similar in the second equation. I'm going to divide out 2 from every single piece of that equation, and then I'm going to move over this negative sum of y sub i's to the other side by adding it over. So in the second one, I would end up getting a times sum I equals 1 to n x sub I plus nb, since we divided out the 2, equals, adding over that term, I get sum from I equals 1 to n of y sub I. Okay, so maybe if you want, and call this equation 1, call this equation 2. So we have to find a and b that basically solve this system. Now you could do this by substitution or elimination. I've lined it up pretty nicely for elimination. I've got my a's in line, I've got my b's in line, and I've got my constants in line. And so I could eliminate either variable. When I was doing this, I chose to eliminate b. And so it just takes a little bit of thought and a little bit of algebra to figure out what you would have to multiply the equations by to make that happen. So let's compare coefficients. This one has a sum of xi. This one has an n. So I'm going to need them to be opposites. One's going to have to be positive and one's going to have to be negative. I'm going to have to multiply the first equation either by n or negative n, and the second equation either by the sum of x sub I or the negative sum of x sub I. So I'm going to choose to make the first one positive n. So now I've got a coefficient of n times the sum of xi in front of those b's. But then I'm going to have to make sure I use a negative sum of xi for the second equation. So I'm just trying to equate the coefficients but make them opposites. And now I'm going to distribute. So if I distribute n through to everything in the first one, so this is solve by elimination or substitution. Again, if you don't like doing elimination, you can do substitution. This would give me na sum of, let's see, I equals 1 to n xi squared. Actually, you know what I'm going to do? I'm going to kind of do this all at once. So I'm kind of right now, what am I doing? I'm analyzing, let me get a different color. I'm trying to analyze basically this right here. So I'm going to get, I can factor out an a. So I get a times, I'm going to have n, I equals 1 to n, x sub I squared, minus, I'm going to have sum of x sub I times another sum of x sub I. So that's going to be the sum from I equals 1 to n of x sub I, that whole quantity squared. Now notice the difference between these two terms right here. I want to clarify this. This is adding up the squares of the x coordinates. So x1 squared plus x2 squared plus x3 squared all the way up through xn squared. This one is actually taking the sum x1 plus x2 plus x3 all the way up through xn, computing that entire sum, and then squaring that result. So they are actually going to lead to two different quantities. So you want to make sure you're careful with how you denote that and where you put that square symbol. Okay, so there's my first one. Notice the b's are gone because I have nb times sum of xi, and now I have minus nb times sum of xi, so that's 0. And so now on this side, I'm going to get, let's see, we're going to have n can come out front, sum I equals 1 to n xi yi, and now we're distributing here, minus sum of xi times sum of yi. Similar to what I said on the other side, that's different than taking the sum of the products. You're adding up all the x coordinates, getting that sum, adding up all the y coordinates, getting that sum, and then multiplying the results on this side. So just be careful with how you denote that. This quantity here is different than this quantity here. And then to get our estimate for a, we're just going to divide what's inside the brackets over to the other side. So I'm going to take this quantity and I'm going to divide it over to the right. So therefore, my estimate for the slope, it's going to look messy, but when you do this with actual data points, it's actually pretty easy to compute. And in practice, you'd be using your calculator for this, right? But you want to know, what is your calculator actually computing? This is the formulas your calculator is actually computing, is using these least square estimates, using this multivariable calculus to actually compute the ideal, the optimal slope and the optimal y-intercept. So we end up getting n, I equals 1 to n, of the product xi, yi, minus sum I equals 1 to n xi times sum I equals 1 to n yi, all divided by that entire numerator is getting divided by what I have inside the brackets. So n sum I equals 1 to n x sub I squared minus sum I equals 1 to n of xi, that entire sum squared. You'd have to compute this before you can actually get the y-intercept. So that would give you a formula for figuring out the slope of this least squares regression line. Now to get b, all I'm going to do is I'm going to come back over here to this equation that I called number 2, and I'm just going to solve for b. So I'm going to subtract a times sum of xi to the other side and divide by n. So if I do that, let's kind of work that from scratch. So we had, I'm going to rewrite it. So this was our equation before we used elimination. A times I equals 1 to n xi plus nb equals sum I equals 1 to n of yi. I'm just going to solve for b. So I'm going to subtract a times sum of xi and divide by b. Or I'm sorry, divide by n. So I would end up getting b equals 1 over n times sum I equals 1 to n of yi minus a times sum I equals 1 to n xi. And take a tiny little aside. I want to show you, if you've definitely computed averages before, but maybe you're not familiar with the formula. Anytime in statistics that we take the sum of the data points with either variable, let's use x, and divide by how many data points we computed, this is what's called the average or the mean. And so this, in statistics, we denote x bar. This is the mean or the average of the x data. And you would get a similar result for y sub I. If you did the sum of the y sub I data points and divided by n, you would end up getting y bar. Okay, so in this case, we can simplify this formula for b. This ends up being, if I distribute here, I end up getting the sum of yi's divided by n. So that ends up giving me the average of the y coordinates. And then if I distribute to the second term, I get minus a times the sum of xi from I equals 1 to n, all divided by n, which is x bar. That's the sum of the x data. And so my estimate for the y-intercept is actually the average of the y data minus the slope I would have computed from over here using this giant formula times the average of the x data. And so here we go. This is the kind of the punchline. Here's my best estimate for the slope. And again, it looks more complicated than it actually is because we're writing it in general, right? And this is my estimate for the y-intercept, which looks quite a bit simpler. And now the last thing to really think about is, well, how do we know that this is minimizing the sum of squared errors and not maximizing it? Now, the first way of thinking about that is intuitively. You really, these errors could grow without bound. If you were to, keep making the line get farther and farther from the data points, that sum of squared errors would continue to grow without bound. So there really would be no maximum. So the physical nature of this problem really guarantees that it's a minimum, but we could use our second partials test to really confirm this, right? If we calculate that Hessian. So let's do that. I want you to actually see that this does confirm it's a minimum. Now, in order to do this, I'm going to give you a small hint. This would actually require a little bit of proof by induction, which is a skill that you haven't learned yet. If you go on to take a proof writing course in college, or if you go into computer science, you'll definitely learn about proof by induction. It's a technique that you could use to prove this inequality. We're going to need to use the fact that n times the sum of xi squared is actually greater than the sum of the xi values all squared. And you'll see where that comes in. We're going to use that hypothesis in a little bit here. So we've already found our critical points. We've already found our estimates for a and b. Now we need to actually confirm that, number one, In order for this to be a minimum, we would need s sub AA, the second derivative at AB, would need to be positive. Okay. But also, and we'd probably be calculating this first actually, so let me relabel these. I'm going to call this number 1 and this number 2. We would need to make sure that our Hessian, our d value at AB, is greater than 0. If the Hessian's greater than 0 and the second partial derivative of a, s sub AA, is greater than 0, then we know it's a minimum value. So if I calculate s sub AA at AB, come back up to my function here, let's see. Lots of math. Original function was a few pages back. Okay, second derivative, here was our first derivative right here. So this was s sub AA. If I take the partial derivative of that partial derivative with respect to a, I'm going to get sum of xi squared. That's going to be the coefficient there. Or sorry, 2 times the sum of xi squared. That would be the coefficient in front of a. And clearly, since you're adding up a sum of squares and multiplying by a positive 2, that has to be greater than 0. That doesn't require really any further justification. S sub BB, if we go back to our original function, let's see, here was S sub B. The partial of that function with respect to B would just be 2n. That would be the coefficient in front of B. And now we need our Hessian, which is going to require the mixed partial. And we are assuming that Clause's theorem applies here. So the second partials, the mixed second partials, are assumed to be continuous in this case. This makes sense because we're doing polynomial data fitting. Polynomials are continuous even when you take their partial derivatives. S sub AB, if I go back to SA and take the partial with respect to B, what would that be? Time for a cheesy joke. I'm laughing. I don't know if you're laughing, but I'm laughing. S sub A. Oh, I'm sorry. I mislabeled this before. This was SA. Sorry, not S sub AA. With respect to B, would be 2 times the sum of xi. We're looking for the coefficient of that term right there. So 2 times sum of xi. Okay. And so now let's calculate our Hessian. D. Okay. I'm going to arrange it as a matrix. Remember, you don't have to. But this would be SAA, this would be SBB, and then this would be my mixed partials, SAB. So as a determinant, this would be 2 times the sum I equals 1 to n xi squared, 2 times sum I equals 1 to n x sub I, 2 sum I equals 1 to n x sub I. The off diagonal has the same element there, right? Because by Clause's theorem, these are equal, and then 2n. And so now, here we go. Here's the punchline. If I compute this, I end up getting 4n sum I equals 1 to n x sub I squared minus 4 sum I equals 1 to n xi, that whole quantity, squared. And I can factor out a 4, and this is where we'll use the hypothesis. N sum I equals 1 to n xi squared minus sum I equals 1 to n xi, that whole sum squared. By the hypothesis, we were told that this first component is greater than this second component. Well, that means if I take the difference, that difference has to be positive. So by hypothesis, or by the hint, I guess I should say, this is greater than 0. And so what we've just proven, therefore, is that this Hessian, this d value, is greater than 0. So to sum up, SAA of AB is greater than 0, and the Hessian at AB is greater than 0. So this implies that AB produces a minimum value. Ooh, there we go. of our function s, our sum of squared errors. Okay. All right, so look, just a chance to apply it a little bit so you can see how this works in practice. Let's actually fit a random set of data. There's no real world context to this data. You could easily go online and find some data sets and try this out too. But I'm going to first show you by hand what it would compute to. Then I'll show you on the calculator how you could confirm this. And then we're going to go to Desmos to finish out. So here's my data. Here's x1, y1, x2, y2, x3, y3, x4, y4, and x5, y5. So in our case, n is equal to 5. We're using a sample size of 5. So things I'm going to need to compute this slope and y-intercept, I'm going to need the sum of xi's. So if you add up all the x coordinates, 0 plus 4 plus 5 plus 8 plus 10, you get 27. I'm going to do these fairly quickly because you can pause me and confirm these yourself. If I do I equals 1 to n of x sub I squared, 0 squared plus 4 squared plus 5 squared plus 8 squared plus 10 squared would be 205. Definitely using the calculator to do that. The sum of y sub i's in this case, 6 plus 3 plus 0 minus 4 minus 5 actually ends up being 0, which will make some of the calculations a little bit easier. And then we are also going to need our sum of products. I need the sum of the mixed products of the x and y terms. So if you take 0 times 6 plus 4 times 3 plus 5 times 0 plus 8 times negative 4 plus 10 times negative 5, you get negative 70. Okay, so now, remember, we have to calculate A, and then we're going to calculate B. So using my formula that I highlighted on the previous page for our estimate for the slope, we would end up getting, if we look back, our formula was we need n times the sum of products, so 5 times negative 70, looking at the next part, minus the product of the individual sums, so minus 27 times 0, all divided by, I think it was n times the sum of xi squared, so 5 times 205, minus the sum of xi all squared, so minus 27 squared. And if you throw that into your calculator, you would get negative 175 over 148. So there's my estimate for the slope. And then my estimate for the y-intercept would be, remember it was y bar minus n times x bar. And so this would end up, or I'm sorry, it was y bar minus a times x bar, I think. Let me see. Yeah, because we were basically solving for b in this case. So this should be an a. Y bar minus a times x bar would be, well, y bar would be 0 divided by 5, right? Or I'm sorry, yeah, y bar would be 0. We summed up the y's. We got 0 divided by 5, so 0 minus a, negative 175 over 148 from over here, subbing in. And then x bar would be 27 divided by 5. And so therefore, we get that b is equal to 945 over 148. So there's my slope and y-intercept estimates. So the least squares regression line, to sum up, and we're going to graph this in a minute, would be y. Now, in statistics, we don't need to get super formal here, but in statistics, because it's a line of prediction, it's a line of best fit, we typically put a hat symbol above to make it known that we're using predicted y values. But again, we're not in a statistics class, so this is just to give you a little bit of insight into data science and stats, but this would be negative 175 over 148 times x plus 945 over 148. This would be the best possible linear model that gets the data points as close to the line of best fit as possible. It's going to minimize the sum of those squared residuals, the sum of those squared errors. So let's actually put this into the calculator so that you can see in practice how this actually works. So last part of this is a little bit of technology. We've done a lot of the calculations that we need. So I'm actually going to show you on Desmos and on the calculator. Let's start with the calculator to verify this. So if we go to our calculator here, if you go to Stat and you go to Edit, just hit Enter. If you have data points in here already, you can hit the up arrow and hit clear, and then hit the down arrow, and then hit the right arrow to go to L2, hit the up arrow, hit clear, hit the down arrow. That'll clear out whatever data you have in there. And I'm just going to enter the X data first. I'm going to hit 0, hit enter, 4. I'm just entering the data points from the example. 5, hit enter, 8, hit enter, 10, hit enter, and that should do it. Hit the right arrow and go to list 2 and enter the Y data. 6, hit enter, 3, hit enter, 0, hit enter, -4, hit enter. Oh, I think it treated it as a minus sign. Oops, because I'm using the keyboard. Yeah, you want to make sure that you're hitting the negative sign. There we go. -4, and the last one was -5. Okay, boom. Okay, so let's go back now to our home screen, second mode. We've got the data entered. I'm going to go to Stat. I'm going to go to Calc. I'm going to hit the right arrow to go to the Calc menu. And I'm going to go to the option number 4 that says LinReg, in other words, linear regression. And there's 2 options. You could use 4 or 8. I like option 4 because it gives you the slope first, then it gives you the y-intercept, which falls in line with slope-intercept form that you learned about in algebra class. If you use option 8, just notice that they're giving you the y-intercept first, and then they're giving you the slope. So I like option 4 because it's not as deceitful. And then it's going to ask you what list you stored the data in. The default should be L1 and L2. If that's not listed, to hit list 1, you would hit second L1, or I'm sorry, second 1. Scroll down. If you don't see L2 there already, hit second 2. You should get an L2 that pops up. Leave frequency list alone. I'm not going to store the regression equation, but I'm going to calculate my estimates. Okay. So we get -1.182432432 and 6.385135135. So basically what the calculator did is it ran through this program that it has kind of in its memory, has all of the partial derivatives and all of this process for using that second derivatives test that we were learning about and that we just computed. So I'm going to put the fraction versions in that we got and compare them to the estimates on the screen. So if I do -175 over 148. Okay, there was, I believe, what we got for the slope. Let's double check. -1.182432432. Let's see. There it is. There's our slope, and let's confirm the y-intercept. 6.385135135. 945 divided by 148. There we go. There we go. So that confirms the slope and the y-intercept are, in fact, the best possible slope and y-intercept to produce this least squares regression line. I'm going to go to Desmos. Get out of here for a second. How do I go to Desmos? Desmos. There we go. Okay. What we're going to do is add a table. So if you hit the plus sign and hit table, make sure it says X1 and Y1. If you see 2s there, change the subscripts to 1s. It'll make step 2 here easier. Just going to put the data in as I did before. It's probably a lot easier on Desmos and a lot quicker. Hit the right arrow to get to the Y column and put your Y data in. 6, 3, 0, -4, and -5. Okay. So now I'm going to hit the row 2. And you can't just type in y equals mx plus b or ax plus b. It doesn't read it that way. You have to program it slightly. So you have to make sure that it knows which set of y coordinates you were using. We called this column y1. So you need to hit y, do shift underscore. So shift minus sign, get you a subscript, hit the right arrow, equals. We want a and b was our slope and y-intercept. So a, then I'm going to call x1. So I'm going to type again, I'm going to do x, shift, minus sign, 1, hit the right arrow to get out of subscript mode, plus b. Oh, one quick thing, you don't want to use equals, you want to use a tilde. So do shift tilde, it should be right to the left of your 1 key. Shift tilde, there we go. And you can see, there we go, there's our estimate for the slope, -1.18243, and there's our y-intercept, 6.38514. The R here is what's called the correlation. It tells you how well the Y data is predicted by the X data. The closer it is to 1 or -1, the better the fit. So this is a pretty darn good fit. The R squared is just a way to tell you what % of the dependent variable values can be predicted by this line of best fit. Looks like about 96% of this variation, 96% of this fitting can be predicted by this line. That's pretty good. It's not going to ever be perfect. It can't be 100% because they don't lie. Not all the points lie on the line. I'm just going to scroll out so you can see it a little bit. So here's our visual, right? That looks like, you know, this green dot's pretty close. This one's real close. This one's real close. This one's real close. And this one's real close. So this is the best possible line of best fit outlined here in black. Okay? And there's our 5 data points. All right, so here's where the more independent part of the lab comes in. What you're going to do is you're going to repeat this process, but you're going to increase the degree of the model. You're going to find an elephant of best fit. Okay, that's a joke, but that's pretty funny, right? If you look at that, there's an elephant of best fit. I think that's funny. Okay, just kidding. You're not going to do that. But you are going to look at nonlinear models. So nonlinear models often approximate data better than linear models. For example, a quadratic regression model, a cubic regression model, maybe a logarithmic or an exponential regression model. A lot of times what happens is as you go out to further and further future values of x, the dots end up getting farther and farther away of the line. So it's called extrapolating. As you extrapolate further and further, the errors become larger and larger. Those residuals get bigger. And naturally that would happen because sometimes, you know, growth is not linear. The linear model might be a good fit for the data that you have, but as you start predicting, say, for example, years down the line, maybe you want to predict profit 40 or 50 years from now, the model might only be good at predicting for a certain subset of data, but if you go to a certain point, it might end up, the distance between the line of best fit and the data point might end up being very large. So the models are limited. So this is why nonlinear models might offer a better fit. And so what you're going to do in this task or in this lab is you're going to find a similar system of equations like we did for the linear model, but you're going to do it for a quadratic regression model. So you're going to have 3 coefficients you have to find. A would be the quadratic coefficient, B would be the linear coefficient, and C would be your constant for n data points, x1, y1, all the way up through xn, yn. And again, you're going to want to minimize the sum of squared errors. Now, in this case, instead of ax plus b, we have ax squared plus bx plus c. So in our case, we're going to want to minimize the sum of the squared errors, y sub I minus a sub xi squared minus b sub xi squared minus c of xi squared. And so that's what you're going to be minimizing. You're not going to solve the system for A, B, and C. It's going to be too messy to do that in terms of all of the summations. I'm not going to make you go super in depth with the algebra there, but I do need you to set up a system of equations that you could use to solve for A, B, and C. And so for the reason here, that's why I actually did do the residual here. I did y sub I minus the prediction squared instead of how I did it the first way around. And that's just because I'm not making you solve for A, B, and C here. So setting up the system won't be too bad. And then you're going to solve a problem at the end with actual data points after finding the general system of equations. So I just want to run through what you're going to do. So here's your workspace. This is where you're actually going to compute your partials and you're going to find your system of equations that would help you solve for this A, B, and C value that you could use to minimize the sum of squared errors of this best fit parabola, this quadratic regression model. So you have quite a bit of workspace. Feel free to add an extra sheet of paper if you need to continue. Once you get to the solve or do all the work, you're going to fill in the blanks with the different coefficients, the different summations, or whatever that you found for each of your equations. And you're going to need 3 equations, right? Because you're going to have 3 partials. You're going to have a partial with respect to A, a partial with respect to B, and a partial with respect to C. And then once you find that system, I'm going to have you actually try it out with some actual data points. So I gave you a sample size of 4 data points here. Down below here, you're going to write your system of equations using the data points. So use your formulas from the coefficients here to actually plug in the actual data. And then you're going to solve it using matrices. Now, I think you've done this in pre-calc. So if you know how to do this already and know how to solve a system with matrices, you might not need to watch this part. But if you've never done this before, it's pretty easy to do and your calculator does it for you. There are ways to solve systems of 3 equations by hand, but it gets very tedious. You have to do multiple rounds of elimination or substitution. And again, I don't want this to be a huge algebra exercise. I want you to focus more on the model fitting. Let's just do a real brief example. Let's say I wanted to solve this system of 3 equations and 3 variables. What I would do is I would enter into a 3 by 3 matrix, 3 rows by 3 columns. The first column would be the coordinates or the coefficients for x. the second column would be the coefficients for y, and the third column would be the coefficients for z. In a second matrix, B, I would enter the constants on the right-hand side that I want those three equations to equal. So I would do a 3 by 1 matrix, 3 rows by 1 column, 1, 12, 7. Just the numbers on the right-hand side of my equation. To solve that system, what you do is you would actually multiply by the inverse matrix on both sides. So I would end up multiplying by the inverse matrix of A, kind of like, if you're solving an equation, just to give you a little background, if you were solving something like 2x equals 4, you would multiply by the inverse of 2 on both sides, right? You'd multiply by 1/2, which is the multiplicative inverse of 2. You can do the same thing with matrices. So if I was really setting up this system, I'd have 2, 5, 5, 3, 2, negative 2, 4, negative 1, 3, times my desired x, y, z, and this would be equal to 1, 12, 7. You can't really divide over the matrix, so what we do is we multiply on the left-hand side by the inverse matrix, which I would just denote, really, I'm repeating the matrix, right? But then I'm just putting a little -1 above it. And I would do that on both sides. You want to make sure you apply it to the left-hand side. So I'm just going to put a star here. And that's all I'm getting at here. So I'll show you on the calculator how to do this. On the calculator, I'm just going to get my sheet so it's a little faster. I want to have the numbers in front of me that I'm using. So if I go to my calculator, if I want to enter matrices, I go to second x inverse, which is the matrix button. I'm going to scroll over to edit. I'm going to hit enter to edit matrix 1, and I want 3 rows by 3 columns. So I'm going to edit my dimensions to be a 3 by 3, and I'm just going to enter in the numbers in that matrix A. It goes by row, so it's going to go horizontally. 2, 3, 4, then it'll go to the next row, 5, 2, -1, and then it'll go to the third row, 5, -2, 3. And this is not for the data set that I gave you. This is just another example I made up. Okay, we edited matrix A. I want to go back. So I'm going to go second matrix again, or second x inverse. I'm going to edit matrix B. This time I want 3 rows by 1 column. So I'm going to edit the second number to be 1. And I'm going to put in the values on the second side of the equations, the right-hand side. So 1, 12, and 7. And then again, all I'm going to do is on my home screen, I'm going to do A inverse times B. My 3 by 3 inverse times my column vector, my 3 by 1 matrix, will spit out the values of x, y, and z that would solve this system. So if I go to matrix, this time or actually second matrix, sorry. You don't have to edit anything. This time you're just calling the matrix. So hit enter, A, hit the exponent button, and type in -1 so that it knows it's doing the inverse. Hit the right arrow to get out of the exponent. Hit the multiplication symbol, and then same thing, go back to the matrix menu, second x inverse, and this time we're going to multiply by matrix B. And this is going to produce the x, y, and z coordinate that solve that system. Oh, I have an invalid dimension. What did I do wrong? Oh, looks like I forgot to save my matrix B. Okay. I have nothing in there. All right, let's do that again. Scroll down. Oh, you know what happened? I accidentally put it in matrix A. My bad. I'm going to have to do that again. Sorry about that. A was a 3 by 3. Okay. You can skip this part if you already have your numbers incorrectly. That's my bad. 5, 2, -1, and 5, -2, 3. Okay, I think I got it this time. Okay, that's saved. Now I want to edit B. Oh, that's what happened. I forgot to hit the down arrow. I want to edit B. Make sure you hit number 2. There we go. 3 rows by 1 column. And I want to put in 1, 12, 7. Okay, make sure I got my numbers right. There we go. So second mode, get you back to the home screen. Second x inverse, we want A to the power of -1. Hit the right arrow. Times, and then second x inverse, I'm going to multiply by B. Now it'll work. And that would give me my value of x would be 2.098. my value of b would be, or yeah, my value of, well, in our case, we're going to be using a, b, and c. In the example I gave you, this was x, y, and z. So x would be 2.098, y would be 0.258, and z would be negative 0.992. And these might even be able to be, they're probably rational answers. So if we do math, enter, math frac, you can get the actual, yeah, the exact answers are even better. So there's your exact answers. When you're doing the lab, I would prefer that you give the actual fractions. If you want to write the decimals underneath, you can, but you can actually math frac your answers to get the exact coefficients, which is a little bit more helpful. Okay, and so, yeah, so that should do it. So now you know how to solve a system of matrices with a 3x3. You're going to need to do that for your actual system that you're solving for the sum of squared errors function. Okay, so just to summarize what you're doing from here is, again, you're going to find your system using the methods from section 14.7 and using the strategy that we used for the line of best fit. You're going to implement the strategy with these 4 data points. You're going to write your 3 equations similar to what I did here for your system. Now your system's going to be in terms of A, B, and C. You're going to use matrices to solve your system. So fill in the inverse matrix, fill in the column vector, and fill in the resulting vector for A, B, and C. And then on the last page, you're going to actually use those to write your least squares regression quadratic equation, the best fit quadratic line, or best fit quadratic equation. I want you to confirm your results using the quad reg feature on your calculator. It's in the same menu as linear regression that I showed you. Enter your X and Y data into the lists like we did for the linear regression data. Go to Stat, Calc, it's option 5. I want you to also graph your results on Desmos to see the best fit quadratic model fitting the data points. And I want you to attach a screenshot of your Desmos scatter plot with the best fit quadratic model superimposed. I gave you an example here. I just made up some data. Here's what you would have to code in to line 2 for it to actually give you the parameters of A, B, and C. So your screenshot, and you can just put it into a Word document, print out a page, and staple it to the end of your lab. It should look something like this. I want to see a good zoom level for your data points and your parabola. I want to see all the data points on there. And I want to see this left-hand menu right here that shows me what you inputted into your data table, and it spits out the correct parameters. Okay, so hopefully you find some use in this. I think it's a real nice application. A lot of times in this class, we just get physics applications. I think it's nice to see some examples of data science and statistics because it is really one of the most growing fields. And for those of you, I know some of you might be interested in going into a field like that or computer science where you're still going to be looking at data and looking at algorithms with data. So just a really cool application of multivariable calculus in the statistical field. So if you have any questions, please reach out. Go back. This video is public to you, so you can go back and watch parts of it that you need to. But that should help you successfully complete the rest of this lab. Okay. Happy mathing, happy statting.